I'm starting now.
The broadcast is now starting. All attendees are in listen-only mode.
Welcome to the third session of DBA Fundamentals for March. Today we have another SQL Skills consultant, teacher, Jonathan Kehayias. He'll be talking about deadlocking for mere mortals. Obviously you know that since you signed up for it. I've got a few other things to go over real quickly because I don't want to take time away from his presentation. The people that pay the bills are Century One. They're our sponsor and we really appreciate them. I'm going to go over one thing a time at each presentation. One of the things that I think that you really need to check out is the answers.sqlperformance.com. You can send them questions and they'll give you tuning advice. If you download the Plan Explorer, which is an awesome product, you can make copies of the execution plans and it will obfuscate any personal information, file names, databases, whatever, and you can send that to them. They can give you suggestions for that. That's an awesome feature you need to take advantage. Virtual group news. I think I said this last time and I've got it wrong again. Shane's last name has two L's in it. He's got a Slack site going right now that we can get to that is a new form of interaction that apparently a lot of people like to use. I haven't used it that much. That's why Shane is heading it up for us. If you want to sign up now, you can go to that link. You can sign up and our site is DBA Fundamentals. PASS has multiple virtual groups and SQL Skills is doing a great job of helping out, doing presentations for a lot of them over lots of different topics. So go to I don't have the link up here, but if you go to the PASS site, you can get to the virtual group site, and there's tons of topics you can choose from, as well as lots of different global languages. Here's some of the sessions we have coming up. Another person from SQL Skills, Glenn Berry, actually two in a row. One of them is down under. The first one is his DMV's, Dr. DMV's Troubleshooting Toolkit. It's one of the best sessions we've ever had. This is the second time we've had it. He had it 3 years ago. He updates all of his DMV scripts for each version of SQL that comes out, so there's going to be new stuff. Then he's going to be doing one on IO system subsystem performance down under. Be sure and check those out. Brent Ozar will be giving, I think he told me this was the first time he'd given it outside of a class, how to triage SQL Server emergencies, so that should be great. And you can do the reading and find out all the other ones that are coming up. Women in Technology have one right after this session that should be a great one. Kaylin Delaney, seeking SQL Server secrets, and then Irish will be doing another one. This is their continuing, and I lost the date there, but I think it's in March also. They are focusing on sessions for the month of March. We're giving away a $350 Amazon gift card for everybody that has attended in January, February, March. You get one entry for each time you attend one of our sessions. I'll be giving that away in the next few days once we go through and tally everything. And we'll be starting up another one for April through the end of June. SQL Saturdays are another great way to experience PASS education. Go to SQLSaturday.com, enter your location, and it'll show you the closest one and dates, and hopefully you'll get to that before one has already been done in your area. These are awesome events. You pay for your lunch usually, and you show up. You have lots of great sessions you can attend, and vendors pay for everything. They'll have a lot of freebies, but in addition to that, you get a lot of great free education. These sessions are recorded, and SQL Skills is always great about getting the scripts and slides to us immediately after the session. You can get that and access to the recordings within a day at our website at this location, or you can go directly to our YouTube site if you don't care about the scripts. Okay. Today we have Jonathan Kehayias. I had to ask him how to pronounce that. I should have heard that. I've heard his name enough. I just have a mental block about it. He's a SQL Server Most Valuable Person, MVP, and a Microsoft Certified Master. He's presented at multiple conferences, including past SQLIntersection, SQLRally, SQLBits, and VMware Open Forum. He's one of the more detailed and expert level people on. He's good across the board, but there's just certain topics that he's just outstanding on, and he prides himself as being one of the best, if not the best, in the industry. And deadlocking is one of them. Extended events is another, and I'm sure their performance tuning, troubleshooting is fantastic. Anyway, he's going to be giving us a session on deadlocking today. So I'm going to turn it over to him after stumbling through that. Let me change the presentation, and I promise you his presentation will be less disjointed than my starting.
All right, so
You got it yet?
should be able to see my screen now.
There you go. Yes.
All right, so good afternoon. This is Deadlocking for Mere Mortals. My name is Jonathan Kehayias. I do work with Paul and Kimberly, Aaron and Glenn and Tim at SQL Skills. My email address is jonathan@sqlskills.com. It's on the screen. I always say if you have any questions about the content, feel free to contact me. And if you have an interesting deadlock that you're having issues with troubleshooting, feel free to shoot me a copy of the graph, and I'll be happy to help out. I collect deadlock graphs. I have a bunch of interesting ones that are one-offs that I haven't ever seen again. But every now and then somebody who's sat through one of these sessions will pop up and say, hey, were you serious about the offer to help? And I absolutely am. It might take me a day or two to get back to you, but I definitely will respond to your email. I might ask for some additional information or ask some specific questions, but I always say that I've never found a deadlock that I can't offer a solution to, but I've found a lot of developers and DBAs that don't want to make the system changes that would be required to eliminate their deadlock. So if we can continue through this, hopefully at the end of this session, you'll be well versed with what's necessary for troubleshooting deadlocks, but if you have an issue or one that doesn't seem to make a lot of sense, feel free to shoot it to me. So I do work at SQL Skills with everybody else. We do a variety of work from consulting to instructor-led training in our immersion events. We also record classes for Pluralsight and put a lot of our training content online. We do some remote DBA work, we speak at conferences, and we have our insider newsletter where you can get additional information or updates from Paul about what's going on. So in 2017, we have a number of classes for our immersion events. A lot of our Chicago classes have actually started to sell out, but there are some seats available in a few of those. We also have more information about that available on our website, and Paul introduced a new client discount for remote consulting for a single instance health check that makes it a flat rate of $29.95 to have somebody at SQL Skills collect information and send you a report of everything that we find wrong or incorrectly configured for your server and how you would go about correcting that. So like Steve said, my name is Jonathan Kehayias. I am a consultant, trainer, speaker, author with SQL Skills. I've been with the company just over 6 years at this point. I just crossed the 6-year mark and into my 7th year, and I've contributed to a number of books on SQL Server over my time working with it. And if you are attending this event, Paul, if you email him, paul@sqlskills.com, and use this subject line user group pluralsight code, you can get a free 30-day code that will allow you to access all of the 145 hours of SQL Skills content that's available on Pluralsight. However, Paul is diving out of the country right now, so it might take him a week or two to get back to you with that, but if you send him an email, he will respond and send you a code that will get you access to the Pluralsight library for SQL Skills. So in this session, we're going to talk about everything you need to know to prevent or troubleshoot deadlocks. And I always start off with with a joke and say, use no lock on all select statements. Because I've seen this pervasively used as answers to forum questions over the last 7 or 8 years. And this is usually where I say, any questions, thank you for attending, and it's kind of a funny joke, but I always come back to this slide and say, this is everything you don't need to know to prevent deadlocks. In certain conditions, this will work, but there's a lot of reasons why this is not the answer. So usually, anytime I see that, without having any further knowledge of what your system does, this can be very dangerous. So it's something to avoid, and if you actually go through and troubleshoot and understand what's happening with a deadlock, it's a lot easier to come up with a better solution. So this is not the answer. So what we're going to talk about as a part of this session is first an initial review of what locking is in SQL Server and the different lock types. We're going to talk about what a deadlock is as a reminder so that we can make sure everybody has the same basic understanding of what's contributing to a deadlock or what's happening with one. We'll talk about how we collect deadlock graphs in SQL Server. There's a number of different ways, and they all have their own pluses or minuses depending on which version of SQL Server you're on, so we'll talk about that. And then we're going to go through what I call the anatomy of a deadlock, where we're actually going to trigger a number of deadlocks that are very common. We're going to take a look at the deadlock graph. We're going to go over what's happening with that deadlock, and then we'll talk about how we go about resolving deadlocks once they have occurred. So some basic terminology. Inside of SQL Server, a transaction is going to be a unit of work that's performed within the database. Locks are the synchronization mechanism used by the storage engine on a resource that protects them from having changes made by multiple concurrent transactions simultaneously. Every lock has a lock mode, and that defines the level of access that the other transactions will have while the resource is actually locked. Blocking is anytime a transaction requests a lock in a mode that is conflicting with a currently held lock, and it has to wait for the other lock to be released for it to gain access to the resource. And then a deadlock is when two transactions block each other while trying to acquire locks on resources that the other transaction holds in a conflicting mode. And it basically becomes a circular blocking chain that will never be resolved unless something happens inside of the engine. Now, locks in SQL Server occur at different levels of granularity. At the lowest level, we have our row or key locks, where a single row is locked either inside of a heap or a index. That's the difference between RID or key. Above that, we have page level locks, and that's where a single page in the database gets locked. We have Hobbit or partition level locks. We have object or table level locks, where the entire table gets locked.
Hello, Jonathan? John? We lost your sound, unless it's just me. Hello?
The engine tries to balance the number of locks versus having the maximum amount of concurrent access. And the engine can decide to start with row level locking, or it can start with page level locking. And in certain conditions, if you exceed either the lock count threshold or internal lock memory pressure is triggered, it will do what's called lock escalation. And lock escalation always goes from row to table or page to table. It never goes from row to page to table. The exception being if you have partitioning, and you can enable partition level lock escalation. And it will go from row to partition, and other partitions may still be available for concurrent access in a conflicting mode while just that one partition is escalated to. So locks are also acquired at multiple levels of granularity to fully protect the lowest level resource. So if we're accessing a table, we're going to acquire a schema-based lock or metadata lock on that table. We're going to have a lock at the table level, a lock at the partition level, page level, all the way down to the row. And this is what forms what's called a lock hierarchy in SQL Server. And to demonstrate this, if we think about an operation that's going to affect just one row on the sales order detail table in AdventureWorks. So we do a delete. We're going to start with an intent exclusive lock on the table itself. And then we're going to have an intent exclusive lock on the page. And what the intent lock does is signals that there is a lower level lock, and it prevents something from escalating to a full table lock that would conflict with the lower level lock. And finally, we'll get an exclusive lock on the row that's going to be affected by our operation, and it can perform the delete, and then the locks will be released. So Martin has a question about when are page locks actually used? As I recall that normal transactions escalate read key locks to partition or table locks. So what's the use case for page locks? The engine actually can decide what level of locking it will use. In certain cases, you actually run into deadlocks because the engine decides not to use a row lock. It uses a page lock. And when the engine will do that, usually is, as I understand it, is when it's going to be reading multiple concurrent pages and utilizing all of the records that are on those pages. And it will choose to take a page lock so that it has a lower number of total locks, because a single page, depending on the definition of the schema, it could have as little as one row on it or as many as a few thousand, depending on how small the table is. So you can also force page locks using the page lock hint. And if you do index reorganization instead of rebuilds, that requires page level locks. And if one of the things that you'll do in a deadlock that involves page locking potentially would be to disallow page locks on the index definition so that it has to do row locking or escalate. And in conditions like that, where you might do that for a deadlock prevention, you would have to enable or alter the index to allow page locks before you could do a reorganization on it. Otherwise, you'd have to rebuild it. So there's different conditions, but it is possible for a query to use page locks instead of row locks just as a default. It's up to the engine how it decides to do that. Now, lock compatibility is how different lock modes either conflict with each other and create blocking, or allow concurrent access to a resource based on them not conflicting. Inside of the books online, there's a very, very large lock compatibility matrix. It takes up almost the entire screen, and it covers every lock type that exists inside of SQL Server. For the purposes of this session and for the purposes of deadlock troubleshooting, you don't really need to know that much information. You don't need to know about all the different lock types. The basic lock modes that are most commonly seen are going to be intent shared, shared, update, intent exclusive, shared with intent exclusive, or exclusive. So if you look at this, an intent shared lock allows other intent shared locks. It allows shared locks, update locks, intent exclusive locks, shared with intent exclusive, but it doesn't allow exclusive locks. Usually you find your intent locks at the page, partition, or object level when there is a lower level lock that is being acquired. So an intent shared, you would have a shared lock on either a row or a page that is covered by the object that the intent shared lock is on. If you have an intent exclusive, you have an exclusive lock somewhere down the line that is being acquired, or that has been acquired and is currently being held. So George has a question. Once the row has an exclusive lock, will it release its intent exclusive lock on the page? No, it won't, because that intent lock at the page, if we go back one slide, is what tells other operations they cannot acquire an exclusive lock on that page. It signals that there's a lower level lock that would be blocking for that. So if we look at, in this case, we have the intent exclusive lock. If we look at our compatibility matrix, if somebody tried to run a very large select statement against sales.sales order header, and it required lock escalation, they would be allowed to initially start accessing the rows with intent shared locks at the page, or I'm sorry, at the table level. But once they tried to escalate to a full shared lock, that's not compatible with that intent exclusive lock here. So it's going to get blocked until this operation completes and that intent lock is released. The intent locks are only released when the transaction completes. They're held for the duration of the operation when there's a lower level lock that's in place. So a deadlock is a condition when two or more processes are holding locks on resources and are waiting for the other one to release its locks to progress, or where two or more processes are waiting for locks on resources in a circular chain. So if we look at, we have process A, process B, resource 1, resource 2. Process A will acquire a lock on resource 1. Process B acquires a lock on resource 2. And then process A, while holding the lock on resource 1, tries to access resource 2 and is blocked because it's conflicting with the lock that's held by process B. Process B then tries to access resource 1, but because process A is still holding its lock, it becomes blocked, and this is where we have what's known as a deadlock. This will never resolve itself because they're both waiting persistently for the other one to release locks, and they won't release their locks until they've completed their operation, which requires the blocking lock or the lock that's being blocked. So some misconceptions. One is that deadlocks are a bug in SQL Server. There are a couple of cases where that is actually accurate, but more often than not, it's not correct. I've also seen people say that deadlocks cannot be prevented. That's not true. Like I said at the start of the session, I've never found a deadlock that I can't provide a solution or a change that would prevent the deadlock condition. I've ran into a lot of DBAs and developers and vendors that don't want to make changes to their system or code. Using no lock on all select statements is the best way to prevent deadlocks from occurring. That's dangerous advice for a lot of different reasons that I won't get into in this session, but that doesn't hold true when you have a deadlock between two update statements, for example, because there's no such thing as a no locked modification to data unless you're using in-memory OLTP, and the locking semantics for that are different. But when we're talking about just standard tables, standard indexes inside of SQL Server, if you make a data modification and every one of them was prefixed by DTA or underscore DTA. And every time what happened is every time they ran into a deadlock, they would submit whatever query through the database tuning advisor and take whatever index it recommended and create it. And a lot of them were overlapping, a lot of them were duplicates, and that's a lot of wasted performance for having to maintain all of those indexes. And there's other ways to resolve those kind of issues typically. And the last one, troubleshooting deadlocks, is a complex task that requires an experienced developer or administrator. It's actually very easy. It doesn't take a whole lot of effort once you actually have worked through and understand what's happening with a deadlock, which is why I like presenting this session. Now, deadlock detection inside of SQL Server. The lock monitor thread in SQL Server is a system thread, and it's what is solely responsible for doing deadlock detection. And what it does is every 5 seconds it initiates a search to identify and resolve any deadlocks that exist. What the lock monitor thread does when it does a deadlock search is it walks the entire lock stack inside of SQL Server, and it looks for any tasks that are blocked. And when it runs into one that's blocked, it does a recursive search to identify if cyclic blocking exists that is forming a deadlock condition. Every time it detects a deadlock, the search interval gets decreased from the default of 5 seconds down to as fast as every 100 milliseconds based on how frequently deadlocks are occurring. And this is so it can identify and resolve deadlock conditions much faster. And then if it doesn't find any deadlocks during a periodic search, it slowly starts to increase that interval back out to the 5-second default. If a deadlock is detected, it assumes that the next lock waits will also enter into a deadlock cycle, and it will automatically trigger a secondary deadlock search. So if a true deadlock is occurring, it will be detected immediately and it will be cleared inside of the system. Now, deadlock priority is something that can be set by any user in their session. All they have to do is set deadlock priority, and it controls the way the engine responds to, or the lock monitor thread responds to a deadlock condition existing. It's not possible to stop somebody from setting this. So I usually say be very careful with how you use deadlock priority. When I was brand new to SQL Server 12, 13 years ago, I was an application analyst, and I had a responsibility for generating reports for the CEO of the company I was working at. And some of the reports that I wrote were really, really nasty, like 4 or 5 cursor deep loop-based processes that were trying to apply a monetary amount to things that were going wrong inside of the system. And one day while I was running this 2-3 hour long report, I got an error 1205, your transaction was deadlocked and selected as a victim. And I started doing research on the internet, and I found out about this great thing called deadlock priority, which became my new best friend. And I figured out that if I set my deadlock priority to high, I never got that error again. But what I didn't know is I was actually dictating that anybody else that was running something in the system that I would deadlock against is actually what would get killed. And that was a lot of the functions that our customer service team was doing. And they constantly had to call people back to reset up things because their operation was selected as the deadlock victim. And after a couple of weeks, our database administrator came in and he goes, "What are you running? You're killing a lot of stuff in the system." And I was like, nothing. I was working in Microsoft Word at the time. And he's like, "What's running in Query Analyzer?" And I pulled it up and he goes, "Who told you to set deadlock priority high?" And I said, "Well, I had this problem and now I don't." And he goes, "Yeah, but you're killing everybody else in the system. Stop doing that." So I always use this as a warning because you can choose to set a higher deadlock priority for important transactions, and that ensures that those transactions will never be selected as a deadlock victim. However, what I usually recommend is to set deadlock priority low on something that is potentially going to result in, be a participant in a deadlock if you can't eliminate the deadlock entirely. And the reason that I like setting deadlock priority low is it allows me to use try catch, and I can say if this is going to cause a deadlock or this is participating in a deadlock, I want this operation to be picked as the victim, and I'll use try catch and retry my operation potentially, but it makes it so I can guarantee that this is something I can control, and I can limit what the impact or gain control over making sure that the code that I want to fail is what's going to actually fail. A good example of that is if there's SQL agent jobs that potentially would result in deadlocks due to transactional replication, way transactions get applied to subscribers potentially. Usually those are the types of scenarios where I'll set deadlock priority low and control what's going to happen so that I can retry the operation that I chose as the victim, rather than letting the system decide who's going to be the victim based on the other criteria. So Jacob asked, how can we prevent developers from setting high deadlock priority? Code review is the only way you can. There's no way to stop a user from changing their deadlock priority if they have Management Studio or Query Analyzer access. The default deadlock priority is normal. So usually when you use set deadlock priority, you can do set deadlock priority high, set deadlock priority normal, set deadlock priority low, or the scale is -5 to +5. You can set a numeric value that the books online covers to control what that actually is going to be set to. So Jacob, we see the deadlock issues when we're importing lots of records in the system and updating records based on the new values. Any recommendations to prevent this? Only if you can send me a deadlock graph. There's no way for me to answer that just in the session. I need to know more about what's happening that contributes to that. Could it be, Martin asked, could it be beneficial to set allow page locks to off on an index? People in my workspace are afraid of page locks leading to less concurrency and more deadlocks. That's a big it depends, Martin. Setting allow page locks off for an index is one way that you could deal with deadlocks, but it puts a lot of limitations in place because you could actually, depending on the way you access that, that index, it could result in more lock escalation, which would create blocking issues potentially. There's no one-size-fits-all answer to that question. Why is an intent-exclusive lock compatible with an intent-exclusive lock? So in general, intent locks are compatible with all other intent locks because all the intent lock specifies is that there's a lower level lock of a specific type. So an intent exclusive means somewhere further down the hierarchy there's going to be an exclusive lock. An intent shared, somewhere further down the hierarchy there's a shared lock. If you look at the lock compatibility matrix, the intent locks are compatible with each other, but they are incompatible with the other lock types. So if you have an intent shared, it's incompatible with an exclusive lock. If you have an intent exclusive, it's incompatible with a shared lock, because you can't have a shared lock at the same level as an intent lock. That means that you're conflicting further down. So that's why they're compatible with each other. Gordon asks, when a lock becomes a
Hello, John. You may have your audio may have dropped out. Hello? Hello?
you get the update lock initially, and then it's converted as the modification occurs to an exclusive lock that is then held until the transaction completes. Why? So Jay asked, why do they get deadlocks when they do an index rebuild? I would have to see the deadlock graph to be able to explain it specifically to you, but it's essentially reverse order access of what's being used during the two operations. And if you can send me one of the deadlock graphs to my email address, I'll be happy to look at it and explain it to you. Jirish asks, how does transaction isolation level affect deadlocks? Isolation level affects deadlocks. We're actually going to talk about this a little further in the session because it changes the way locking behavior works inside of SQL Server. And in certain conditions, you can use snapshot isolation with row versions in TempDB so that readers don't block writers and writers don't block readers. And that could be a resolution for deadlocks. If you have a system where no lock would work for a reader-writer deadlock, where a select statement is being killed, you could set read uncommitted isolation for the session that's running the select statement, and it would have the same effect as no lock across that scope of execution. So the isolation levels do affect what's happening. Serializable isolation for distributed transactions or things that you've set specifically into serializable isolation can lead to very specific types of deadlocks that we're going to talk about one a little bit later with the demonstration. So deadlock victim selection. When a deadlock is detected by the lock monitor thread, the lock monitor has the job of choosing which one of the threads is going to become the deadlock victim. The deadlock victim is then killed, rolling back its transaction, which releases its locks, and the client will receive a 1205 error that gets raised by the lock monitor thread. The deadlock victim is always selected based on two specific criteria. The first is deadlock priority. The log monitor thread checks the deadlock priority of both sessions, compares it, and the lowest priority session is the one that gets selected as a victim. If both of the sessions have the same deadlock priority value, then the transaction that is the least expensive to roll back, which is based on the number of transaction log records that have been generated, is what gets selected as the victim. And that's the default behavior. Everything has normal deadlock priority unless you start playing around with it. And whoever has the most amount of transaction log generated is going to be the one that wins because it has the most amount of work that would have to be undone. So to collect deadlock graphs in SQL Server, there's a number of different methods of doing it. You can use trace flags. Trace flag 1222 was introduced in SQL 2005 and higher. And if you're on 2005 or higher, 1205 and 1204 are just really painful for you to have to try and dig through the information for. So they're there. I keep them as a reference because there are people that use SQL 2000. If you're on SQL Server 2000, you have to use a combination of trace flag 1204 and a SQL trace output to piece together all the information that you need to troubleshoot deadlocks. And I usually joke around and say good luck if you're on SQL 2000. It's not a very easy task. The additional information that Microsoft provided in 2005 and higher for deadlock analysis makes it a whole lot easier to do. You can also use SQL Trace or Profiler to gather the deadlock graph event. You can use event notifications or WMI to automatically respond to deadlock graph events. Usually I use event notifications for systems that have random deadlocks and just hook database mail into it. So it collects the deadlock graph and it'll shoot me an email message so that I know a deadlock just occurred, here's the graph, and we can go through troubleshooting it. And starting in SQL 2008, you could use extended events for deadlock analysis. However, I always say this is not a viable solution until SQL 2012 for a lot of reasons. But on 2012 or higher, you don't have to turn anything on to do deadlock analysis. The XML deadlock report is a part of the system health event session. It's written to a file in the file system, and you can go retroactively into system health and grab the XML deadlock graph for a deadlock. There is a caveat there. My coworker actually just ran into this today, where extended events, the timestamp on the event might not match the actual time that the event occurred. And there's a skew with one of the timers that SQL Server uses for generating what the timestamp is, where it can be hours to days off for every event that's being generated, depending on how long the system has been up. It's a bug that has a connect item that's filed for it. It's been filed for a long time. It's something I run into periodically, and the only thing you can do is add an additional action to the events to collect the system time, which is the actual clock time of the server where the event was generated, as an additional column. And there's a blog post on my blog that talks about the incorrect timestamps for events in extended events. Now, the reason that I don't say 2008 R2 is viable with extended events is the system health event session only uses a ring buffer target, which is in memory. The window of XML, first you have to shred XML, which I know everybody just loves to do, but the window of XML that can be output is limited to 4 meg of serialized XML from the binary event data. Well, the target itself holds 4 meg of binary data, and it doesn't take a lot of math to figure out that 4 meg of binary data serialized in XML form isn't going to fit in a 4 meg window in the DMV. So a lot of times people will email me, and I actually have a blog post that talks about this as well, and say, I had a deadlock occur, I'm using your scripts for extended events, I'm not getting anything back. Why? And my answer to them is, wait a while. If you wait, eventually the event will fall in that 4 meg of output XML, and you'll be able to see it. The events are there. There's just no way for the engine to output them through that ring buffer target, which is why in 2012 or higher, I say go to the event file. This problem exists in SQL 2012, 2014, 2016. It's a limitation of the DMV. So these are the different methods that you can use for collecting deadlock graphs. And what we're going to do really quick is we're going to go set these up. So first thing I'm going to do, there's a reset script that will clean anything that's residual up from the demos. So first thing we can do is enable trace flag 1222, and I'm actually going to turn all of these different options on so that we can compare the graphs. Excuse me. And if we look at DBCC trace status, we'll see that 1222 is turned on, but it's only turned on for this session. It's probably pretty unlikely that I'm going to have this exact session selected as a deadlock participant. So what we need to do, turn it off for the session and turn it on globally by including -1. And if we look there, now that is globally set for any thread inside of the system. The other way we can do it that I like to use is event notifications. I usually create these inside of MSDB because MSDB is already configured and enabled for Service Broker, and event notifications piggyback on the Service Broker platform. So we'll create a queue to hold our events called Deadlock Graph Queue. We're going to create a Service Broker service to receive You can also configure WMI inside of SQL Agent to monitor for deadlock events. I don't set this up because inevitably I leave it in place or something gets left behind when I'm doing other demos, and the WMI inside of my VMs under certain conditions just drives more CPU usage. So I usually don't ever set this up, but it is another method that's out there where you can use WQL. And what you do is you create a WMI alert in SQL Agent. You're going to query the SQL Server events namespace in WMI for the instance. So MS SQL Server being our default instance. You're going to do a WQL or WMI query language. It's very similar to SQL. Select star from deadlock graph being the event we want to get. And then that alert is going to fire a job. And all our job does is replace the WMI text data and insert it into a table inside of our database. And one of the other things to note with WMI piggybacks on event notifications for the mechanism of delivering that event to the Windows management instrumentation to trigger the alert. So I just keep it as simple as possible, and I usually stick to event notifications or extended events. So the first deadlock we're going to talk about is a reverse object order deadlock, where two processes access objects in reverse order. So this is probably the easiest deadlock demo to trigger. All you need is two tables, table A, table B. We're going to update table A and process A, which is going to require an exclusive lock to make the modifications. And then we're going to start another process that's going to update table B, which also requires an exclusive lock. Then we're going to try to update table A from our second process, and that's going to require an exclusive lock, which will create blocking. And then we go back to the other process, tell it to update table B, and now we have a deadlock. And whichever one generated the least amount of transaction log is going to be selected as the victim. It'll be rolled back, allowing the other operation to acquire its lock and succeed. So we're going to set up a demo database, but before we do that, I'm going to pop out SQL Profiler, and I always caveat this: you shouldn't run Profiler directly against a production server. It's a very easy way to kill performance. However, for demonstration purposes, the only event that I'm going to add to this template is the deadlock graph event, so that I can demonstrate collecting deadlock graphs through SQL Trace, and we can export the XML so that we can compare it. So we're going to create a database. If it exists, we're just going to get rid of it first. And in that database, we're going to create a table called table A. We're going to load 1,000 records into table A, add a clustered index on column 1. We're going to delete rows 105 and 106 for specific purpose of one of the demos later on. We're going to create table B, add one row to it, create a non-clustered index on column 2 of table A, and then we're going to create two stored procedures, one to do an update and one to do a select that will create a key lookup or bookmark lookup operation inside of its execution plan, which is one of the things that contributes to a specific type of deadlock. So the first deadlock that we talked about, the reverse object order deadlock. So we're going to run update table A. We're going to affect every row. We're going to do it inside of a transaction so that it holds the lock. Then we're going to update table B, which only has one row, and attempt to update table A. And at this point, we have standard blocking inside of SQL Server. To trigger the deadlock, we'll attempt to update table B. And that was not supposed to happen. Management Studio crash. So here we have our 1205 error. Transaction process ID 52 was deadlocked on lock resources with another process has been chosen as the deadlock victim. Rerun the transaction. So if we jump over to Profiler, you'll see we have a deadlock graph. And Profiler and Management Studio, if you have a deadlock graph, will actually lay it out in a graphic form. And you can see this is our deadlock victim. We can see what statement it was running. And you pay attention to the arrows. The arrow points to the owner and points to what's being requested. So in this case, our update to table B owns an exclusive lock on table A and is requesting an update lock on table B. Our victim owns an exclusive lock on table B and is requesting an update lock on table A. So what I usually do is go to Export, extract SQL Server events, extract deadlocks, and we're going to save the deadlock graph out to a file. And if we come to Management Studio, we can do Open, go up one, and if we open that file, it will show graphically here as well. But what I like to do is actually look at those in Notepad. So let's pop that open. And I go straight to the XML for almost all of the deadlock analysis that I do. And the reason that I do that is if you understand the XML format, it's easy to drill into what's happening very, very rapidly. One of the first things that I always do is I take the victim process identifier and I replace it with the word victim. So now I know this is my victim process and what it was running. But when I look at my resources, and I'm going to actually pop this open in Management Studio so we can do some collapsing. But when I look at my resources, I can see very clearly that the victim is waiting for an update lock on table A, and the victim owns an exclusive lock on table B. It just makes looking at all the different process information a lot easier when you have one tagged as who the victim is. So what we're going to do is come over here, and if we execute XP read error log to read our error log file, scroll down to the bottom, here is our deadlock graph information, and it's output by trace flag 1222 into the error log. No. If we go to MSDB and receive our deadlock graph event notification message, we'll get the XML and we can pop that open here. These are all the exact same deadlock, it's just different ways of looking at the information. And if we query extended events, notice we got nothing. Well, the reason we got nothing is the event isn't in that form XML window. I always have my virtual machine running for a little while so that I can demonstrate that. And what we want to do is go to the System Health Event session, view the target data for the event file, and if we come all the way down, here is our deadlock. So if we open this, now, multiple ways of getting the information, but if you look across the different formats, so this is our deadlock graph from the error log. The only thing that's different is it's not wrapped in XML tags. It's the same deadlock graph that you get from event notifications. This is the same XML that we got And for a multi-victim deadlock, in extended events, you'll get one deadlock graph. In trace flag 1222, event notifications, trace, WMI, you'll get a separate deadlock graph for each of the victims that occurred, and they'll have their own victim laid out, and there's nothing that really ties the multiple victims together without understanding or seeing the pattern. So extended events does a lot for making analysis of that a bit easier. But here in Management Studio, if we have the XML, we can collapse the process list. And again, I would just do a replace with the word victim. Replace all. So here we can see we have a key lock and a key lock. Look at who our owners are. Look at our objects and indexes. And it's very easy to start piecing together what happened here. And in this case, it truly is a reverse object order deadlock. And where I see these a lot of times is where two developers develop processes that touch the same tables at different points in time, and there's really no rhyme or reason for why one chose to affect table B and then table A, and then the other chose to affect table A and then table B. And just changing the order of operations is a really easy way of correcting these. So let's look at another. I think this one's probably more common from my experience, but I know other people would argue with me on that. And it's either a key lookup or a bookmark lookup deadlock, where we have a select statement that is very highly selective that can access a non-clustered index. But the non-clustered index is non-covering. So to get the columns that are needed that aren't part of the non-clustered index, we have to do a lookup back to either the clustered index or a heap. So this is a very timing-based deadlock, and we have a process that's doing a data modification, insert, update, delete. It's going to require an exclusive lock at the clustered index level, and almost simultaneously a highly selective select begins that requires a shared lock on the non-clustered index. But to do the lookup, it's going to have to do a shared lock at the clustered index, and that's where we get blocked. Since we're changing data in the clustered index by our process A, we have to maintain the indexes. So it's going to have to do an exclusive lock on the non-clustered index, and this is where we get our deadlock scenario. I like to call this the SharePoint deadlock, because index crawls with SharePoint. Anybody that has SharePoint knows they're very prone to deadlock conditions, and this is the type of deadlock that occurs. And the last time that I worked with SharePoint, it only took 2 changes to 2 indexes to eliminate the deadlocks during index crawls, but product support doesn't allow you to make those changes. It's an unsupported change, and the feedback from Microsoft was it's not a problem because the application handles the deadlock and retries the event, which is true. It just is always something, at least at the time that I was working with SharePoint, that product support would require investigating the deadlock errors that were being reported at the farm servers, even though we looked at them 10 times already previously, and the end result was nothing was going to be changed. So in this case, the select statement is who gets selected as the victim, because select statements have 0 transaction log records associated with them. So it's killed, it's rolled back, and it allows the other process to complete. So if we look at this, we're going to execute our bookmark lookup select, and it's just going to run in a loop so that it actually hits the timing condition to generate the deadlock. But if we generate our execution plan for this, you'll see we have our key lookup here from our non-clustered index to our clustered index. And then the other deadlock component is a statement that's going to update every record as well. So we're going to start that running. We'll start this running. Got to run it in a loop. So it took about 4 seconds for the deadlock to be triggered there. 1 second, and it'll start to be faster and faster. And this is the lock monitor thread backing off or reducing the search interval and doing more periodic searches because we've had more deadlocks occurring. So let's go back to retrieving. And I'm going to pull from event notifications again, just because it gives me easy XML to work with. So we're going to take our victim process, replace it with the word victim, collapse the two process nodes up, and let's look at our resources here. So when I'm looking at deadlocks, the first place I always go to is the resources, because I want to know who owns what and what objects are being accessed. And in this case, when we look at the object, both of them are table A. One's a clustered index, one's a non-clustered index. And this is the marker that would tell me to go look at the victim process and see, did it have a key lookup or a bookmark lookup there. So if we're looking at this, our winner has requested a exclusive lock on the non-clustered index, and it owns an exclusive lock on the clustered index. So that's just normal operation. It has to acquire the exclusive lock to update the pointers in the non-clustered index whenever it changes data in the clustered index or inserts a record into it. And then if we look at our victim, it owns a shared lock on the non-clustered index and is requesting a shared lock on the clustered index. And that right there would make me come up to our process and look at what statement's being executed. And here we can see we're running this stored procedure. So if we pop that over into a new window and just go to the database, generate an execution plan, we have a key lookup. So there's a lot of different ways you could deal with this. This is one of those cases that if you created or modified the index so that it was covering, we would only have an index seek against the non-clustered index. We wouldn't have this lookup, and a deadlock would be impossible. It's also a condition where if we no-lock that select and we allow a dirty read to occur, then it would not hit the deadlock scenario because the select statement can be no-locked or put under read uncommitted isolation. And it's also a case where if we used row versioning in TempDB, either with read committed snapshot isolation or snapshot isolation for the transaction, for our select, we would use the row version in TempDB, and readers won't block writers and writers won't block readers. So there's a number of ways you could go about troubleshooting this specific type of deadlock that would either prevent it or change the condition to where it actually wouldn't happen at all. So Martin asked, would read committed snapshot isolation help with preventing bookmark lookup deadlocks? Yes, it is one of the conditions that it would help. Larry asked, can only multiple select statements create a deadlock? I have never seen a deadlock where it's only select statements because select statements all have shared locks associated with them typically. So I'm not going to say that it's impossible because as soon as I say it's impossible, somebody will find a way to do it. But to my knowledge, it's not something that should happen, and it's not something I've ever seen a deadlock graph for, Larry. So the next type of deadlock we're going to talk about is a serializable deadlock. And I always call this the BizTalk deadlock. This is where BizTalk's where I usually see this the most. But if you have anything that uses distributed transactions, you can run into this type of a deadlock. And it's based on serializable lock conversions under serializable isolation. And if you recall when we set up the demo, we deleted records 105 and 106, and so we can trigger this type of deadlock. So inside of our table, we have row 102, 3, 4. We're missing is one of the requirements for serializable isolation. At the same time, we have another operation that comes in and says, if not exists, select one from T where key is 106. That's going to acquire a range shared lock on the same exact range because 106 falls between 104 and 107. And because the record didn't exist, we're going to try and insert it. So this does a conversion of that shared lock to a insert lock, and this lock conversion becomes blocked by the other shared lock that's held on the same exact range. Well, since 106 didn't exist, we're also going to try and convert this into a range insert lock, and we have our deadlock condition. Usually whoever started last is who's going to be selected as the victim and rolled back. The other one will succeed. So with this, we're going to start and we have our deadlock victim. So we're going to stop this one, roll back any transaction to release any locks that are being held, and we're going to go back to retrieving. And I'm going to have to retrieve a couple. So let's clear the queue. All right, and we're going to run this one more time. Just trigger the deadlock again. So we're going to pop the deadlock graph open, collapse our process nodes, replace our victim, and look at our resources. So when we look at our resources here, if you see a range lock, the first thing that you're going to want to do is come up to your processes and scroll over and look at what isolation level is being used. And in this case, it's serializable. If you see range locks and this isolation level says read committed, that doesn't mean that they're actually using read committed. It could mean that they're in a distributed transaction that's being handled by MSDTC. The way that you would know that would be to come back this way and look at the transaction descriptor, and it will have DTC as a part of it. If it's a DTC and it says read committed, and I bring this up because it actually happened to me, what happened is the DTC is executing potentially a stored procedure, and at the top of that procedure somebody put set transaction isolation level read committed. Under the covers, a DTC is serializable even if it says that it's read committed. Because of the semantics of distributed transactions, it has to be serializable in the engine. So you're going to see serializable locking behavior. In this case, range locks being what that would be. So here we have the victim owns a shared lock and is requesting to convert to an intent lock, and the succeeding process owns a shared lock and is requesting a conversion to an insert lock as well. So this is an interesting scenario where there really is only a couple of ways that you would deal with this. One would be to retry the operation that failed. That's usually what happens. But the other would be to change your lock mode for the operation. So if we come back to our original queries and we do with update lock, and we apply that to the process that's getting the initial lock. So instead of getting a shared lock, we're going to force an update lock. And what that will do is two update locks are incompatible. So it will create initial blocking, which is going to affect concurrency some, but we won't ever get a deadlock. So I can run these two operations simultaneously in their loop, and these will run forever. Because SPID 75 will block 76, it'll release its lock, 76 will acquire its locks, it'll block 75, it'll release its locks, 75 will acquire, and they work around each other. So under serializable isolation, where the locking semantics are going to have range locks and you have lock conversions happening like this, this is usually how I would go about reducing or preventing the deadlock condition. So we'll stop these two and issue the rollback to make sure that there's no open transactions. And the last one we'll talk about is the multi-victim deadlock. So a multi-victim deadlock happens when you have something that's running in repeatable read isolation mode or where you're specifying hold lock as a part of transactions. So we have multiple processes that are selecting from table A under repeatable read or utilizing hold lock in an explicit transaction. We have an update that runs to update table B. Our select processes need to access table B, so they need a shared lock that's incompatible with the exclusive lock. And then our update needs to access table A or modify table A, which requires an exclusive lock. And we have our deadlock condition. And in this case, since these are both selects and have no transaction log generated, they're going to be selected as the victims. They'll roll back and our update will succeed. So this one's somewhat tricky to be able to trigger reliably. So if you're going through the demos and you're having issues with it, there are notes inside of the demo scripts for the order that things need to be run. So you're going to run this in two separate windows. So we're going to run to here, run to here. We're going to run our update, and then we're going to come back and do our select against table B. Let's roll this back. We're going to roll everything back because one of the windows didn't work right. Okay, so we're going to start over. We're going to run this. We're going to run this here. We're going to do our first update. Create blocking by querying table B. So those two processes are blocked. And if we trigger our deadlock, they're both killed. And if we look at our trace information, so here we have one deadlock graph for one of the selects. We have a second deadlock graph for the other select. And this is where extended events becomes really useful. So if we go to our system health event session, it hasn't buffered out yet. There we go. So there is a dispatch latency that happens with events to the file in extended events asynchronously. So here you'll see we have our victim list, and we actually have both of our victims listed together. There's only one deadlock graph, and it ties everything together. Where if we look at our other methods, so if we go to event notifications, where is script 4 got closed? Let's run that one more time. I've only seen it once in a live system. It's kind of contrived how you would have to go about creating it. But it is a way that extended events makes deadlock analysis easier. Now, the bug in SQL Server that I talked about are intra-query parallelism deadlocks. It's a deadlock between parallel threads in the same session that's executing using parallelism. Generally, this is going to be associated with a bug in query optimization that may or may not be easily fixed by the optimizer team. Or it could cause query plan regressions, and it may be too risky for Microsoft to fix. And the workaround for this is to reduce the degree of parallelism using option max stop, or rewrite the query or do tuning of the database indexes to change the plan that gets used. The way you identify this is you look in the deadlock graph, and all of the processes have the exact same SPID. If you have more than one SPID in the processes for the deadlock graph, you have a deadlock that involves parallelism, but it's not an intra-query parallelism deadlock necessarily. And you would just troubleshoot that the way that you would a serial deadlock between two serial query executions. If you look at the deadlock graph, you'll also see the deadlock resources will be on Exchange event resources only for an intra-query parallelism deadlock. And again, I've run into these a few times consulting and in my own systems before joining SQLskills. Rewriting the query to get a different plan is one way that you can avoid this. And the deadlock happens on a merging exchange. I believe the repartition streams operator is where it occurs. And the threads just end up deadlocking against each other during that operation, and waiting for producers, waiting for consumers in a manner that allows it to result in a deadlock. Now, some ways to resolve deadlocks. Change indexing to cover queries is one way. Enabling read-committed snapshot isolation or utilizing snapshot isolation is another way. Writers won't block readers, readers won't block writers. Changing the isolation level potentially, or using locking hints to force specific lock types to prevent lock conversions if you're running into serializable deadlocks. What I prefer to do, though, is more defensive coding, where we're going to catch and handle any deadlock errors. So we can use a try-catch block to handle 1205 errors. The error number function will return the error number that occurs. ADO.NET can also handle deadlocks when they occur by catching the SQL exception that gets raised for the 1205 error. And if you probe the number property of the SQL exception, it will have the error number that gets raised. And then I usually go to retrying after a deadlock. So custom retry logic can be implemented either in Transact SQL or your application tier. And you can retry any operation that was selected as a deadlock victim. And it usually will succeed on a retry because the locking scenario that leads to the deadlock occurring is very short-lived inside of the system. The retry logic that you put in place needs to be coded so that you don't get into an infinite loop in case it consistently runs into an issue. And then make sure you do logging of the deadlock to allow for diagnosis or potential prevention of issues in the future. And this is where I usually, if you can't make changes to your application to eliminate a deadlock, this will at least make it so it's not having a negative impact to your end users potentially. So if we look at handling deadlocks. So this is a basic template. I've actually used this with a number of clients. I've sent it to people that have sent me questions about how to do retry logic. And this works for 2008, it would work all the way back to 2005. If you're in 2012, instead of doing raise error here, I would just use throw. That would be the main change that I would make. 2012 or higher, you don't need to raise the error, just throw. We'll push it back out if you need it, if it's not a deadlock. But what we do is we set a value for retries for. We're going to try our operation. If it succeeds, we're going to set retries to 0, which makes it jump out of the loop. If it fails, we're going to catch the error, check is it a 1205. If it is, we're going to decrement retries once. You can do logging here. In this case, it's just saying a deadlock occurred. It's going to retry. And then it'll go through the retry. When retries equals 0, we're actually going to end up throwing the exception back out, because we're not going to continue to retry infinitely. And the same thing can be done in ADO.NET code or any application language for trying and retrying deadlocks. But this is a basic template that is really easy to reuse over and over again. So let's look at answer questions. I see deadlocks happening occasionally inside one transaction, which has a parallel execution plan. What could potentially do about this, or do you know a reason why this happens at all? So this is potentially a SQL Server bug on SQL 2008 Service Pack 4. It could be an intra-query parallelism deadlock. I'd have to see the graph. You'd have to look at the graph to know whether or not that's actually what is occurring. If it's all on the same SPID, then that's what it is. And I wouldn't be surprised on 2008 Service Pack 4 that you're running into that. I used to have a couple of demos for intra-query parallelism deadlocks, but Microsoft has corrected or changed the optimizer behavior and eliminated those as bugs, so they don't happen anymore. It's one that every time I've had a good demo of it, within like a few patches, the demo no longer works. So if you want to send me the deadlock graph, I'll be happy to look at it. If it is an intra-query parallelism deadlock, you can the workaround, even if you open a product support case, they would tell you to set max stop 1 using option max stop 1, and it won't deadlock. Or sometimes you don't have to go all the way down to 1. If your server level max degree of parallelism is like 8, you could try 4, try 2, then try 1. It varies system to system. I'm surprised I don't see this serializable deadlock more often in my environment. We make extensive use of linked servers. Just because you use linked servers doesn't, it depends on what you're doing across the linked servers to whether it will enlist a DTC or that would put it into serializable isolation. So the use case, it varies. So some key takeaways for this session. Most deadlocks aren't a bug in SQL Server. Once you understand how to read the information in the deadlock graph, they can usually be prevented. The XML is my preferred method of going at it. If you have Plan Explorer from Century 1 installed, it includes a deadlock viewer that graphically lays out the deadlock graph. That also makes digging into the information very easy. I'm just, I guess, old school, or it's hard to teach me new tricks because I always go back to the XML. It's just what I'm comfortable with, and it's what I enjoy working with the most. Don't blindly put no lock on select statements or add covering indexes for every query just to prevent deadlocks. Look at the root of the deadlock and see what's happening before you make any changes. And whenever possible, use defensive coding with try-catch blocks to handle the deadlock. Retry the victim, which is basically what SharePoint does. It does it as a part of its framework. Logs an error, and it continues on. So I hope you enjoyed this session. If you have any further questions, feel free to ask them. There's a bunch of resources. Bart Duncan worked at Microsoft, and he was originally the person who blogged about deadlock analysis going all the way back to SQL 2000. And his blog still has the most information on deadlock analysis, and he actually answered a question I asked him years ago. execution memory grant-based deadlocks and how you would troubleshoot those. So unless there's any remaining questions, that is the end of the presentation. I'll make sure I get the scripts over to the organizers to share in just a few minutes.
Good deal. Thank you. I'm glad I'm able to talk. My headphones have been going in and out during the entire session, so I'm going to really enjoy going back and listen to it on YouTube. So anyway, thanks, John. We loved it. I'll be looking for that stuff. Thanks for a very informative and very, very good presentation. Thank you.
Yep, no problem.
Bye.